I am speaking on behalf of the entire project that made this happen. There are basically everybody in the world can profit from this. About 10,000 professional astronomers can use it because that's everybody. And it took about 20,000 of us to build this beautiful thing and put it up into space, including people from 3 space agencies and I don't know how many private contractors and universities to do this. So there it is in space, a great golden hexagon mirror made out of 18 smaller hexagons, all fitted together very carefully. The umbrella protects it from the heat of the sun, the earth, and the moon. It can be cold so that we can observe the infrared light, and so it does not emit its own infrared light. So it's cold way out there in space. But why are we doing this? Well, I have these questions. Many of us have these questions. Where did we come from? What's the history? Are we the only ones here in the entire universe? Or if not, where are the neighbors? Is life a remarkable coincidence, a miracle of some sort, or does it always happen given the chance? The opposite would be this thermodynamic imperative. So how far can we go? Well, I don't really know that answer, of course. We know we can get to Mars. We don't have a way to get people back just yet, but that's not impossible. But we astronomers, we travel at the speed of imagination, so we can see everything out there that we can see, and we can tell you the stories, and we're going to tell you some of them today. So we've been working on these problems for a long time. Even more than 2,000 years ago, people were aware of the idea. Something is advancing my slides. It must be me. So 2,000 years ago, people knew about the atomic theory. They knew that things could be made out of tiny invisible particles, that they would assemble into patterns. We would names because we're people, we talk about things, and then they would fall apart. And so the mystery of this all was available in general terms to them, but they didn't know quantum mechanics. So they didn't know yet that the little invisible particles have shapes of their own that stick together in particular patterns, such as molecules, such as genetic molecules, such as the entire machinery that makes the genetic molecules readable by cells. So they had no idea of that, and we're only beginning to develop that understanding. We know that happens. We don't know how it happens, even though we know the genetic code is there. So this is where I started off my scientific career. I grew up on this farm. It's a farm of Rutgers University in far northern New Jersey, about a mile from the Appalachian Trail. And it was a beautiful and clear spot. I could see the sky at night, which I can't do from here in Washington, D.C. Anyway, there was a laboratory there beyond the barn where the bulls lived. And so it's where I started thinking about science. And I learned a lot of it from books that came around on the bookmobile that arrived at the farm every 2 weeks from the county library. So it was a good place to get started despite the disadvantages of not having access to competitors and scientific laboratories of other sorts. Anyway, that's where I got my start in far northern rural New Jersey. So what happened back then, in addition, in 1946, well, there's Lyman Spitzer, a picture of him standing on the mountain. He was the person who wrote a report for the Rand Corporation just after the end of the World War II that said we should build telescopes in space, and not only to look down, because you can do that in the Earth and learn about your opponents, but you can also point them upwards. You can even make them, as he imagined, very large, polish a shape into an asteroid so it's a mirror, and you might be able to detect planets around other stars. Very far-sighted person. So here's something else that was going on in 1946, more or less. This isn't exactly the right year for him. That's Sir Fred Hoyle, who gave the name to the Big Bang Theory, and has confused the heck out of everybody since because it's exactly the wrong name. But we have not been able to reverse this name. It's a sticky name. So anyway, we'll deal with that a little bit later. And then in 1946, I appeared. Well, that's not exactly what I looked like in 1946. But anyway, that's my history of getting started in all this. I wanted to give you a context for what else was going on. In 1948, Alfred and Herman in this picture were talking about the Big Bang. Ralph Alpher on the right wrote his thesis about the Big Bang and predicted that there should be cosmic microwave background radiation at a temperature of about 5 degrees. And 300 people came to his thesis defense because it was a very exciting topic. But nobody went to look in 1948. I don't know whether they could have done it in 1948, but they didn't. So what else went on? Well, around 1953, I went down to the Museum of Natural History with my parents, and I saw the planetarium show. We're hoping, the world was hoping we would see these canals on the surface of Mars because it was closer than ever, but we didn't see them. Now we know they were actually the arteries and veins in the back of the observer's eyeballs. So we didn't know that yet. And then in 1997, the Sputnik went up, and suddenly this country was petrified that not only could we be bombed by nuclear bombs from aircraft, we could be bombed from above. So in that year, suddenly the United States got even more serious about supporting you and me and other science and engineering people to protect us from the Soviet Union. And I guess we can say it was successful for a time because we're still here, and none of the bad things that were thought about at the time have happened. So what else went in? In 1958, NASA was created by an act of Congress, and there's the document showing that we were created. And here's Jack Kennedy announcing at Rice University that we are going to go to the moon.
And they may well ask, why climb the high? Why 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
Well, my goodness, I hope you could hear what he said. But at any rate, here is James Webb, the man. He was the person who was leading NASA at the time. And he went to the president with a plan to go to the moon, and we did it. 7 years or so after that speech, there were people walking on the moon, which to me is a completely astonishing accomplishment. Not only did he do that, but he started off somewhat against the president's wishes and said, we need to have science, Mr. President, and we send out probes to the planets, and started astronomy in space. So now, stepping back to the basic astronomy, how do we know what we're looking at? Of course, we look back in time, and you do every day, although you don't think about it. You look at things as they were when light was sent to us, not as they are now. So look at things very far away, you look very far back in time, then that's our astronomer's secret, because we're the only ones who actually do that for a living. So how do you know how far you're looking back in time? We do surveying of the sorts that the ancient Greeks and civilizations in India and China would have all understood. You survey with triangles, you compare the brightnesses of standard objects, and you can calculate how far away things are. Then we couldn't have done this in those days, but now we know how to measure velocities of things going toward us or away from us from the Doppler shift, because the chemical elements in the stars produce marks across the spectrum. They spread out the light of the star into a rainbow, and there are dark bars across it, usually, that come from the particular chemical elements. And what we often find is that distant stars and galaxies are running away from us with enormous speeds. And so this is now something we can measure and use. So back in 1929, Edwin Hubble drew us his first graph, which showed that the universe is expanding. So what does that mean? It means actually each of these dots represents a galaxy, hundreds of millions of stars, hundreds of billions of stars, orbiting a common center usually, held together by gravity. And what he found out here is that the farther away they are, the faster they're going away from us. Divide the distance by the speed, and you get the apparent age of the universe. So this was the first time anybody ever had any evidence whatever that there was an age of the universe, that it wasn't either zero or infinite, it was something, a number that you could possibly measure. As it turns out, this was predicted already in 1927 by Georges Lemaitre, who's a Catholic priest in Belgium, as well as having a PhD from MIT, using his mathematical skills to work with Einstein's equations. So Einstein didn't believe them, but it turned out to be true. So there it is, the understanding that there was something very different and unique. The universe was young, and now we call it the Big Bang, which confuses the heck out of everybody. So after my Berkeley stint, where my thesis project to measure the Big Bang actually failed to function properly, I got a chance to work for NASA in New York City, and there it is on the left-hand side. You can't really see the lab, but that building was devoted to NASA, upstairs from Tom's Restaurant. So some of the older folks might know that Tom's Restaurant is in the TV series Seinfeld. Anyway, I bicycled to work and had a good time doing it. And when I was there, I said, okay, boss, my thesis project didn't work. We should try it in outer space. And I said that because NASA said, there's an opportunity to propose new satellite missions. I said, let's do this. So we called up our friends. We wrote our proposals. I thought that will never work, but it did. So 15 years later, after the napkin sketch, there it is in space. It measured the cosmic background radiation in two really important ways. One is, as Alex mentioned earlier, it has the exact spectrum that it should have. It has something that's completely featureless. It has no spectral links, it just has a temperature. The other thing that it has is we made a map. How bright is it across the entire sky? And there are hot and cold spots. And they're not very hot and not very cold, but they're there. And so that turned out to be even more important because it told us not only the Big Bang a real thing, the universe really was hot when it was young, but also details about what should happen next. So here's the map that we got, the universe as it was when it was about 400,000 years old, as seen with our satellite. And the hot and cold spots are very faint. The whole temperature of the map is about 2.7 degrees Kelvin. The faint hot and cold spots are about a part in 100,000 of that. So very, very, very hard to find. So a true technical accomplishment. What the result was, now we know the initial conditions of the universe in the sense that we should be able to take this information and predict what would happen next. How do the galaxies grow from that primordial material? Well, it's not so easy. So of course you have to go make measurements and take pictures, and you have to get more detail about this particular map. As so Alex mentioned, WMAP was flown, the Planck mission was flown into space, and many thousands of astronomers have devoted their lives figuring out the meaning as well as the measurements of these spots. So of course I got to go off to see the King of Sweden. I showed my graph a lot of times, and been having a lot of opportunities for public speaking ever since, as well as lots of parties. So that was fun, but was already working on the James Webb Space Telescope at this point. So I kept on doing that. And so before I talk about that, I want to talk about how the public has been misled by the journalists about the Big Bang. So many people tell me the Big Bang is everything compressed into a point, and it is just not. It is the opposite. So if anybody wants to see my longer version of that, there's something on edge.org, and you look up John Mather on edge.org, and you can. But I don't want to tell you all the stories today because I want to talk about the Webb telescope itself. So to get to the Webb, first we built the Hubble telescope, and here it is in outer space. In a couple of months, it will be 33 years old in space, and it is working beautifully because, among other things, we've sent up astronauts 5 times to upgrade it and fix it, as well as to repair the things that broke. But we are so thrilled with it. And on the other hand, astronomers knew immediately, and even before it was launched, that it couldn't do everything. So they wrote a little book and they said, please build a new telescope that's even more powerful than that one. And that was going to be the James Webb telescope. So here it is, a little more words about it. The telescope is 6.5 meters in diameter, about 21 feet, which is much bigger than the rocket. That tells us that you're going to have to fold it up to get it into the rocket. The telescope has only half the mass of the Hubble, and that's because we have to push it way out into space, and the space shuttle was no longer going to be available. It could never go there anyway. So 7 times the collecting area, half the mass, is a huge engineering challenge. And by the way, it has to be cold and folded up to get it into the rocket. So when Alex was telling you about all the things that could go wrong, it was mostly about the unfolding process, which I will show you in a moment. And it was a little scary for everyone. Anyway, the project is led here from NASA Goddard Space Flight Center in Greenbelt, Maryland. We have many other parts of NASA we're working with, as well as the European and Canadian space agencies. Our biggest contractor out of many is called Northrop Grumman Space Systems, and they're located near LA Airport. We have 4 major instruments that come from around the world. Near-infrared camera from the University of Arizona, a near-infrared spectrograph from the European Space Agency and their contractors, a mid-infrared instrument from Jet Propulsion Lab and Europe, and the Canadian instrument package includes a fine guidance sensor, which we use to lock onto a star and make sure that pictures will be sharp, and also a spectrograph. The telescope is operated from our system, the Space Telescope Science Institute in Baltimore, which is the same place that we work with for the Hubble telescope. So it's tried and true, and the systems were copied over as much as possible from the old one to the new one. So the telescope is way out there. You can see that it's big. It's also extremely cold. That big golden hexagon is a temperature of about 50 Kelvin, 50 degrees above absolute zero, so that it doesn't emit its own infrared light. It was launched on a European rocket called the Ariane 5, and I'll show you its launch in a second. Anyway, the original goal was, a requirement was 5 years of mission life and a 10-year goal, and we can do a lot better than that. I'll show you in a bit. So there's the launch. It was actually in the daytime, 9 o'clock in the morning in French Guiana. And of course, why does it go from there? Because it's on the equator. It's a good place for launching rockets. It also is a piece of France. So it's a French rocket. So there it is. And you would not know from watching that it was going to be a completely perfect launch with exactly the best possible place we could put it, which means that we didn't have to spend any extra fuel just after we got out there. And so we're expecting to have at least 20 years of mission life, which is a miracle as far as I'm concerned. Of course, how do you get miracles in something as complicated as this? You check and check and check. You measure and check and measure and check and rehearse and practice and check. So this is where we're putting it. Now, it is orbiting around a place called the Sun-Earth Lagrange point, or L2, which was actually discovered in 1750 by Leonhard Euler, who had a pencil for to work with. There are 5 of these places in the solar system where if you hang out at those spots, you can move around the sun once a year with the Earth. So that's an interesting place to be. We choose L2 because from that general area, the sun, the Earth, and the moon are all in the same direction, and the one-sided umbrella will protect us from the heat. So here is our scary movie. When we landed a probe on Mars, they had 7 minutes of terror. So we had a couple of weeks, 5 layers, so that the telescope will be cold even if there are holes in it, which there are, of course, by now, because they're what I call space bullets, little micrometeoroids that will go right through something like that. But anyway, there it is, as no human has ever seen it. If you're an amateur astronomer and you have a pretty big telescope, you can actually find a little dot in the sky where this is. Anyway, that's it in space. So a little bit now about why do we want to do this? Oops, come on. So speaking of space bullets, we're able to make a map of the surface bumps on the mirror to see how different they are from perfect. And there's one quite interesting bump you can see on the lower right hand side here. Not sure if my mouse is going to show you here, but there's a dimple on the mirror on this one that wasn't there when we built the telescope. So we got a micrometeoroid that hit a vulnerable spot. And so we are very fortunate. We've only had one of those in the first year, but if we had a lot of them, we wouldn't like it. So as far as we know, it's not going to prevent us from doing what we want because they're not very common, but they certainly are annoying. So why are we doing this? Well, why do you want a telescope that can pick up infrared light? So here's a picture of a star that's being born. One of the great mysteries of astronomy is how are the stars born? So there is a star seen by Hubble with wavelengths that you can see with your eye. And here is the Hubble picture with slightly longer wavelengths, infrared light. You can see already that the dust grains are much less obscuring, and you can begin to see through the dust cloud and to see the stars behind it and to see the star in the middle with jets shooting out of it. So we already know that seeing through dust clouds is a really good, important thing to do if you want to see how stars are born. You can see things that are too cool to send out their own infrared, their own visible light. So this is an example of a really remarkable system where there is a star blowing up and sending out material into shells around it. And this amazing structure is partly due to the fact that there are stars blowing up. Now, actually, here you can see on the right-hand side with the longer wavelengths, you can see there are 2 stars, but actually we believe there are 5 that made this complicated pattern happen. So when stars blow up, this is an important part of our history because this is one of the ways that the chemical elements that you see around you in the house are liberated back into space so that they can become future planets and future people. So we need to understand this process. So we even have detected this remarkable story. On the left-hand side, you see a picture of shells of dust that have been expelled from a star. And the right-hand side is a model that shows how it happens. 2 stars are going around each other. And when they get close enough, one of them is provoked and sends out this flash of dust into space. So the third reason to study infrared light is that space itself is expanding, or at least if it's not expanding, then at least it seems that distant things are going away from us with great speeds. So let's get a dynamic illustration of that something that sends out blue light, we receive, by the time we receive it, it's actually red. So the graphic isn't still quite perfect, but by the time we receive the light that was sent out as blue, it comes to us as red. So we need an infrared telescope to pick up light that was blue. So now what have we seen? This is a picture that President Biden released on July 11th last year. Our first picture to go, and it shows some astonishing things in it that we were really hoping to find. And so we knew immediately that it had worked beautifully. The big, beautiful thing right in the middle is just an ordinary star. And we're not that interested in that particular star, but it tells us that the telescope is focused perfectly. And these 6 spikes sticking out from the image are just due to the wave nature of light bouncing off the hexagonal edges of those hexagons. In the middle, we see these bright, glowing, gigantic galaxies. Here's one, some other really big, bright galaxies here, which are important to the story because they are so massive that they have the gravity to bend the light that comes past them. So Einstein told us there could be gravitational lenses in space, and there are. These are examples. The gravitational lenses are so strong that actually a light beam from the early universe can be deflected by 1 or 2 arc minutes, which is a pretty big angle, on its way to our telescopes. And we also take advantage of this because they can be magnified. So there are quite a few funny looking things in this picture that are like funny looking arcs. There's one, there's another one over there, something that looks like a strange shaped bean over there. These are multiple images of individual galaxies that are much farther away than the big bright one in the middle. So we're now using nature's additional lenses, nature's telescopes, to see farther and better. with this technique. So one of the things that we do was to find one of those particular ones. This is a particular galaxy that was imaged 3 times in the same picture because it's not exactly a good magnifying lens, it's distorted. But all the same, it shows us a number of details that we never guessed we could ever find. The right-hand picture shows you what are called globular clusters. A globular cluster is something like 100,000 stars that were all formed together, and they have the same age. And it looks like they are all falling in to this new galaxy that's being born way back 9 billion years ago. So this is the story we're now telling about our own Milky Way galaxy. It was probably also formed by thousands of small bits being pulled by gravity to form this wonderful Milky Way that we live in. So combination of objects like these globular clusters falling in with gaseous material falling in, and that's how come we have the way that we have today. Here's an example of galaxies colliding. This is a picture called Stephan's Quintet. There are 5 galaxies in here. The one on the left-hand side in the middle is actually pretty nearby, and it's near enough that we can see little speckles all over it that come from individual stars that we can see with the Webb that we could never see before. In the middle are 2 galaxies. You see these little eyes looking at us, and they're in the process of falling together in the next few 100 million years, and they're surrounded by the gaseous clouds which show where new stars are being born as we speak. The top one actually has a black hole in the middle. So not only is it got all kinds of gaseous material falling into the black hole, but we can now study the details of what's going in, how it's orbiting around, what are the chemical elements involved, are there new stars being born right next to the black hole? And so all of those things are things we're working on as astronomers to understand what is this picture telling us. Here's another beautiful picture called the Cartwheel Galaxy. This is a place where the upper galaxy, one on the left, went right straight through the middle of the big one in the middle. And so what we're seeing is this splash around the big galaxy. That's the result of material being expelled from the center of that galaxy from the Great Collision. So this is a laboratory for us to understand how our stars formed when the gaseous material is disturbed. So it happens. We don't always have a good laboratory because quite often the laboratory is hidden inside a dust cloud. Here's a totally amazing picture that shows us the shape of what we used to think of as an ordinary spiral galaxy here in the middle. And now we take infrared picture, a longer wavelength infrared picture, and we see there's material in the outskirts of that galaxy that's just in the process of forming into new stars. And this galaxy has holes in it, at least as seen in the infrared. So why are there holes in the galaxy? Why does it look like a slice through a sponge? It's because when new stars are born in these less dense regions in the outskirts, the energy that's released from the new stars is so strong that it could push away the material, push away the gas and the dust that's nearby. And the result is a balloon blowing up. And as it crashes into the material that's already there, it prompts the birth of new stars. So we see all these little knots here around the hole that are where new stars are being born. Another good place to study the formation of new stars. Here's one of our most famous NASA pictures. It was known as the Pillars of Creation a long time ago when we just had the Hubble picture. And now we've added in also the Webb telescope picture. And you can pretty clearly see what's going on here. There's a huge wind blowing from the upper right corner down towards the lower left. It's pushing the gaseous material around. And where the material is dense enough, we see these little things that are stubbornly resisting. And some of them are, like this one right here, have just formed a bright star because it's right there at the tip of the dust cloud. So there are a lot of these where you can tell that there's something dramatic going on. Stars are being born right in front of us, and there's a whole lot of them to check out and work out the details. So we've even caught a star being born with its disk orbiting around it. This is right in the middle of this picture is a new star. And then across the way, there is a dark region, which we think of as the future solar system, the dust grains in the future solar system orbiting around that star and blocking a view. So if we were to wait another few 100,000 years, perhaps we might see there's still a disk of material, but also some recognizable planets hiding in there. I'm kind of hoping we might find them soon, but not yet. So a place where a solar system is being born as we speak. So speaking of solar systems, we want to look for planets around other stars, and we have two basic methods. One is to just look for them and see if there's a little dot next to the other star. That's really hard because the stars are so much brighter than the planets. And so it's almost impossible to do that with the tools that we have today, unless the planets are very unusual, very big and bright. The other method that we can do relies on a coincidence, a special orientation of the planetary orbit. If the orbit of the planet around that star is just tilted just right so the planet can go in front of that star, we can notice this as the star will blink. It go fainter for a few hours, and we'll say, I know something happened. And if you watch it for long enough, you see it do it over and over. And so then you can say, not only do I know there's a planet there, I can calculate how long it takes to go around its star. I know something about the star, so I can calculate what is the temperature and how large is this planet. So that's the stuff we've been able to do in the past with missions like the Kepler and the TESS missions. Now we're able to do spectroscopy. So spectroscopy says spread out the light of the star into its colors and see if the amount of light that's blocked by the planet depends on the wavelength. And it could if some of the light is going through the atmosphere of the planet on its way to the telescope. So you can see the effect of dust or clouds or molecules or atoms in those other planets. So our first year, and here's an example of one that we saw. It's called a hot gas giant. So it's like Jupiter in size or mass, but is much closer to its star, so it's much hotter. And this particular one is showing signs of having sodium and potassium and carbon monoxide and carbon dioxide and water, even sulfur dioxide in the atmosphere of that big planet. So we shouldn't be too surprised because these molecules form easily. But so on the other hand, this is a way to understand systems. We may not be able to see little Earths out there, but we can see what their big cousins are like. And so that tells us something, which we will then try to work out the story for you. So we've seen, and of course, in our own solar system, right away we look at the big planets. Here is a lovely picture of Jupiter. Of course, the great red spot isn't red when you can't see with your own eyes at the right wavelength. So we've colored it blue here. We make up artificial colors to show you things because, of course, you have to make one up. The way we usually do it is the shortest wavelength is shown as blue, the longest wavelength is red, and in between is yellow or green. So what this blue planet is showing you is the blue areas are a little hotter than the others. You can see Jupiter now has auroras on the north and south poles. We have direct images of some of its satellites here. We even see that Jupiter has a faint little ring of dust grains orbiting around it that seems to be attached to this little satellite called Adrastea. So we were quite thrilled that we could do this because it's tricky to do. Jupiter is spinning while we're trying to take its picture. And so you can't just say, take a quick picture. Anyway, this is a huge technical accomplishment to be able to take a picture of something that is spinning around while you're watching it. We watched NASA attacking an asteroid. I should say we deflected an asteroid. We hit it with a big double asteroid redirect test to see how much it would move. And everybody that had a telescope that could see it was watching. So here are pictures with the Hubble and the Webb. One of the things that we learned from it was that debris comes out, quite a lot of debris. The result was this little asteroid moved about 5 times as much as we thought it would if there had not been any debris. coming back. So that's interesting. We're learning how to protect planet Earth from little killer asteroids like that one. More work required. We are going to send a lander out to Titan. Titan is of Saturn, and there's a little sketch of the Dragonfly lander in 2034, which isn't so far away now. It's still under construction, but launch isn't so far off now. So here is a we got of Titan with our Webb telescope cameras, and we can see that it looks quite different at different wavelengths. Titan is a fascinating place because it has an atmosphere enough to support the helicopter. It has a surface of ice. It has hydrocarbons, liquid hydrocarbons, and clouds made of hydrocarbons. So if there is any possibility for life to exist based on some other system besides liquid water, then this is a place where nature has done that experiment. So we are certainly interested in this object. Of course, we took a picture of Neptune. It also has rings, and I'm showing you this not because I know what it means, but just because it's beautiful. So there are a lot of things you could follow up with us on the Webb telescope. So of course, you can find everything that we do online. Images are posted frequently, and they come out on our social media sites, and you can find them by Googling NASA images, many other ways. So that's the Webb telescope story. I have a few minutes left. I want to show you some of the things that are coming next, because we're at the end of the story. Astronomers have been dreaming of bigger and better telescopes forever, ever since the first telescope. So the next one that I know of that's going up into space is called Euclid. It's a mostly European project with small pieces from NASA, and it's going up on a SpaceX rocket this spring, I think sometime. I don't know the date. Anyway, it is going to be measuring a lot of the sky, looking for signs of dark matter and dark energy. We are about to start working with the Vera Rubin Observatory, which is also called the Large Synoptic Survey Telescope, in the next year is the plan. And it will take immense numbers of pictures, a few seconds of exposure on each piece of sky. With the upshot, there will be just an uncountable, practically uncountable number of things to look at. They tell us that about 10 million things will be observed every night that have changed since the last time we looked. So some of them will be asteroids, some of them will be variable stars, and something will be a surprise. So this is coming, and by the way, it's named for Vera Rubin, who worked here in Washington and was one of the original workers on the cosmic dark matter. She had lots of good evidence for why it is there, but she didn't get all that much credit for her work at the time, but now she is being recognized. NASA is launching another telescope aimed at dark matter and dark energy, and it's named for Nancy Grace Roman, who was our chief astronomer at NASA for a time. It is going up to look for measurements of the dark energy and the dark matter again, and it also carries a camera that's going to practice looking for little planets around other stars. So it will find some, of course, but it's probably not going to find very many little Earths because it's not powerful enough for that. But it will demonstrate that we know how to do this kind of engineering, and we will try. We'll see what we can do. We, of course, as astronomers, we are always dreaming about the next big thing. So National Academy of Sciences wrote a report for us that said, please build us this thing next. And what they said was, let's build a telescope big enough to see little Earths orbiting other stars. And when I say little Earths, I mean orbiting stars like the sun, and I mean get a little dot next to the other dot. So you can separate clearly the light from the other Earth from the light of the star. We don't have to just depend on that special chance alignment between the orbits so that the planet goes in front of its star. So that will be very exciting when that's up there. It's a very difficult project because, well, we have to make basically perfect optics. But I think it's possible. And so we have already started thinking about it. although we're not really able yet to invest very much effort into it. So coming soon, we hope to have this up in the 2040s or before, depending on what our strategy turns out to be. So maybe the possibility of seeing signs of life on another planet isn't so far off after all. I've also been working with people thinking about the great telescopes on the ground. And of course, you've already heard about them. I'm sure that we have a new generation coming. Two American-led ones, Giant Magellan and 30-meter telescope, and a European one, which is the biggest. It's 39 meters across, almost the width of a football field. And it's made out of over 1,000 little hexagons of glass. Anyway, it's coming along well. And when we have that, then there will be adaptive optics for it, so it can get sharper pictures. And a technique which was imagined back in 1953, but we couldn't build it then. Anyway, so now we will be able to get really sharp pictures with really immense telescopes. And who knows what we'll see. They can't do what we can do in space, but on the other hand, we can't get such a big telescope into space either. So there are a lot of things for the big ground-based telescopes to do. And I've been working on this one, which is called the Orbiting Configurable Artificial Star. If you want to help those giant telescopes focus, it would be nice to have a star where you want it to focus on. So I've been working on that idea. We know how to build it. We know how to launch it. We don't have anybody saying, yes, I have the money for you, but we know what to do. So that's coming, I hope. It's one of those interesting things that falls between the National Science Foundation and NASA because it doesn't belong to either of them alone. But I think it can happen. If we get very ambitious, this is an idea I got some support for. It's called an orbiting star shade. If I could put a star shade 100 meters in diameter into space and put it and hold it in front of the target star, I could cast a shadow of a bright star onto the big telescope on the ground that I just showed you. And if we could do that, we could get a snapshot of another solar system in an exposure time of 1 minute. So I think that would be worth trying. So I think that we might even have a chance to see Earth-like planets and get their spectra to see if they're like Earth. So not impossible, just really, really incredibly difficult as of today. But I have a student challenge open through the Society of Physics Students. So people are invited to send us mechanical designs for how to do this incredibly difficult thing. So then we could get a spectrum of another Earth. And the one that's of great importance here is this blue curve, a synthetic curve, which shows the little spectrum bumps that are due to water and oxygen in the atmosphere of another Earth. Not impossible, just so I guess it's a good place to conclude with how far can we go. So I don't know if we want to send the chat bot to the stars, but eventually the chat bot will be better and it'll say it wants to go to Alpha Centauri. So let's wrap up and I'll have questions. Thank you all for coming and I hope you have some really interesting questions.
Well, thank you very much, John, for that wonderful overview of what JWST has done and your path leading up to it, and also then the view of the future. So we have already some questions that have been sent my way, and let me start in on those, and then there will be other ones as well. Okay, so the first one is that, gravity is limited by the speed of light. So do you have to somehow take that into account when doing your calculations, or how does the gravity's speed affect what you're doing, John? Okay,
well, good question. Basically, the speed of gravity is the difference between Einstein's theory of gravity and Newton's theory of gravity. And it makes some difference to us, but not very much. So practically speaking, for controlling the observatory, it's all been built into the computer software that we use to plan the orbits. Now, when we think about what does it mean for astronomy, then it affects the black holes, which are governed by general relativity and Einstein's equations. and they start to differ a lot from Newton's version. So that's where the speed of gravity comes into us in a practical way in understanding the black holes.
Right, and of course we had this wonderful LIGO detection in 2017 of a merging pair of neutron stars, and it was 130 million light years away, and the gravitational waves arrived at the same time as the light, and that is what essentially proves that the speed of gravity is the speed of light. Okay, the next question, John, is why does the background microwave map show the universe as it was at an age of 400,000 years?
Okay, well, the early universe was very hot and very opaque, which means light waves would bounce off electrons very quickly, so they couldn't go anywhere. When the universe was about 400,000 years old, it had cooled down to a temperature of 3,000 Kelvin or so, at which point the electrons grabbed onto the protons and alpha particles that were there, and suddenly the gaseous material became neutral, mostly neutral, which is transparent. So the light waves were able to keep on going in a straight line without hitting anything for the next 14 billion years. So we see the universe as it was when it became transparent.
That's right. It's a little bit like you're in a fog bank and you can't see very far, and then the fog dissipates or condenses or whatever, and suddenly you can see far away. So
yeah,
very
exactly. Yeah.
So if a mirror segment is severely damaged, can it be aimed away so that it does not affect the imaging?
Yes, we certainly worked that out in advance. Yes, we know how to do that and what we would do, but it would still be a very annoying situation. So we hope we don't ever have to do that.
Right. I know in that first month, it was kind of alarming to have that big micrometeorite hit. And so then the question was, you know, are there many more out there than we thought, or was this just an unlucky, you know, quick hit, but not representative of what we're going to be getting the next few years? And fortunately,
yes.
The latter.
Yes, yeah. It's we actually do get them every month or so, but most of them have very small effects, which don't care about. Right. So we have one that made a big dimple, and that was really annoying, but we've only got the one. And even if we get them every year for the rest of the mission life, we'll still be fine.
Right. And now we point sort of away from the direction of motion so that the speed of the incoming particles and hence their kinetic energy is lower. And so there's not as much bang.
Yes, that's the plan anyway.
Right. Here's another question, John. There's lots of questions coming in. What is the fuel cost for pointing the telescope?
It's actually zero. We point the telescope using reaction wheels, that is to say, big spinning objects that are inside the spacecraft. And when you want to point the telescope, you apply torque to the wheels. So that's how you point the telescope direction. There is a small residual effect, which is that the sun pushes on the telescope and tries to turn it over because there's sunshine, and sunshine has pressure. So every now and then we have to fire the jets to get rid of the angular momentum that the sun has given us.
Great, yeah. And it looks like I'm supposed to say who's asking the question, so I'll do that from now on. Going back to what you also said, the question might have been a little bit also about how much fuel is needed to nudge the thing back to L2 every once in a while, because it does kind of wander away gradually. Can you comment on that?
Yeah, the acceleration, it's easier to say how much acceleration. It's a few meters per second per year. It's an extremely small amount of thrust that we need. Okay. So we could have done it with some other method, but we just use good old chemical the way we always do.
Okay, great. That one was from Chris Owen. All right, now from Paul Lake. If a human were immersed in the pillars of creation or some similar nebulae, what would they see with their naked eye?
Oh, that's a lovely question. I never thought about that. You would see not very far because you would be embedded in this very dense cloud of material. So you would see your own star that you were near because you'd be close to it, and maybe a few others that are not too surrounded in dust. And then you probably would not see the rest of the universe. you would see this glowing cloud that we show in the visible light wavelength pictures, and you might never know there were galaxies out there.
Yeah. Visible light is blocked by all the dust. All right, David Lyon says, great presentation, thanks so much. Question, this might go back to what I just mentioned. You mentioned a technique to reduce the probability of further micrometeorite hits on the telescope sections. Could you describe that technique at high level?
Yeah, basically we know the rate and energy of the particles is more if you're looking towards the direction we're going. In other words, if you're running into the rain, and it's less if you're running away from the rain. So the technique is very simple. Don't look into the rain.
Right, that's right. This way the little micrometeoroids are catching up with the telescope, and so the relative velocity is smaller and kinetic energy is 1/2 mv squared. So let them catch up rather than directly ramming into him. Here's a question from Henry Ganuzzi, who's actually the son of the people at whose place I'm staying at Tahoe, and he's in high school. Why is beryllium used to make the mirrors for JWST?
Okay, well, it's a special material because it's extremely light and it's extremely stiff, and the only competing material is diamond. So that's too hard, so we don't use that. However, it's also tricky. It's tricky because beryllium powder is bad for you. It can become very sick. So the machining of it was done inside sealed machines where every particle of beryllium powder was captured and returned to the factory for reuse. So beryllium also has a special property that it doesn't distort when we cool it down to a low temperature. We really needed that because, of course, we make the telescope at warm temperature, we measure it at warm temperature, and then we cool it down, and it has to be the right thing when it's cold.
Right. Very, very cold. There's a 650 Fahrenheit differential, by the way, between the side that the sunlight hits and the side on which the telescope is on. And only 5 of those thin sheets lead to that 650 Fahrenheit differential. Absolutely astonishing, John.
Yeah.
So hard to believe, but it works. Okay, Charles Laird, alternative view or terminology to the Big Bang?
Okay, well, I'll give you the name that Calvin and Hobbes had in their cartoon. Horrendous space kablooey.
Right. And I believe either Sky and Telescope magazine or Astronomy magazine had a contest, a naming contest. And one of my favorites that was sent into them was Bertha D. Universe. Right?
Yeah.
Bertha D. Universe, right.
So what I actually say is expanding universe, which captures the whole story and it doesn't suggest a firecracker. The trouble with the Big Bang name is it makes you think of a little explosion in a pre-existing space. And we're talking about the infinite expansion in the infinite space.
Right. Okay. Here's another one. Let's see. From David Lyon. You mentioned a technique. Oh, yeah, I did that one already. Sorry. From Donald Ponikvar. You mentioned the proposed guide star satellite to facilitate adaptive optics telescopes. The Department of Defense, with which he's associated, and the international astronomy community has used the natural, oops, my screen was going up, has used the natural sodium layer and a ground-based laser of the appropriate frequency to excite the sodium lines and create a synthetic guide star. Has NASA considered that approach as well? What is the advantage of a physical guide star satellite?
Yes. So, of course, we have been quite aware of these sodium layer guide stars they've been in use and development for decades. But the state of the art doesn't get us all to the shortest wavelengths that we want to go to. So performance is not quite good enough. So it works, but it's not quite good enough. So what are you going to do to make it better? This is one of the choices. You can make more and more and more sodium lasers, or you can try this. So we're hoping that this will actually work. So
Right.
I'm seeing you have a lot of these in the chat, but there were also a Google spreadsheet. Did we get any questions from that?
Well, so what we're asking people, there's a few people with their hands up as well. Post your questions to the site that Carla and Ann mentioned at the very beginning, and that way it'll be easier. Here's one from Roger Sullivan. Jupiter is very bright. Do you have to attenuate its signal to protect the sensitive IR detectors?
No, we don't actually. They are very sensitive, but they don't seem to be much bothered by the very bright object. They do have a temporary response, sort of like your eyes do. When you turn on a light, suddenly you can't see very much. But yes, we do really have an effect.
Okay, John.
Temporary.
Yeah.
Okay, John, I was wondering if you could magically right now make a small engineering change that changes the capability of the telescope right now. Is there anything that you would do?
Oh my goodness! Given the magic wand, I think I would leave it alone. I would just make sure that it keeps on working forever. So maybe I would make sure that we never run out of fuel with my magic wand. But astronomers have already said what they want next for the one. So we're learning from what we have to make it the next one even better and more powerful and do something different.
So here's a question from Charles Laird. How many 100-meter star shades are required to cool our Earth?
Oh, I do not know, but it's too many.
Yeah, some of the geoengineering that we might do in the future. Okay, let's see. So here's one, no name. Are adaptive optics possible to be retrofitted to compensate the newly introduced static aberrations from micrometeorite impacts?
Oh, they're thinking about our Webb telescope, and the answer is we don't do adaptive optics exactly, but we do adjust the telescope. All 18 hexagons can be adjusted with little motors to compensate for the change. So we already do that every time that one hits.
Yeah, that's great. Okay, let's see. That one is a repeat. Carla, are there other ones that have been coming in? Those of you who had your hands raised, if you could post your questions, that might be easier. Either in the chat to everyone or on the form that Anne just sent again. Okay, here's a message. In the pillars of creation, what is the composition of the wind that gives rise to the beautiful erosion features, and what is its source?
Okay, most of the wind that you were seeing is hydrogen and helium, because that's most of the universe. And the reason that it's so hot is bright new stars have just been born. And they're, when I say bright, I mean really, really, really bright, thousands of times brighter than the sun. And some of them are going to burn out in a few million years. So they do all of this incredible energy release very, very quickly. So they have a combination of radiation, that is to say visible ultraviolet coming out, and some of them even have a physical wind that comes right out of the surface. The combination is an immense amount of energy is released into that hot gas there, and that's what's pushing.
Right, absolutely beautiful how it's sculpting the shape of those pillars, just gorgeous. Yeah. John, what are the new results regarding dark matter and dark energy?
Oh, I don't think I've seen anything that's a really new result, but we're getting hints because we're using the gravitational effects of the dark matter in those lensing galaxies. When I showed you the picture, the very first one, most of the focusing that those gravitational lenses are doing is because of the dark matter that's in them. So we are just beginning to understand how that works. We need to make models of how it works. So far, the questions people really want to ask is, well, what is this stuff? And is there only one kind? And so I don't think we've gotten to that point yet. We are able to tell you what it's doing, how much is magnifying distant galaxies. But I don't think we're yet there on what is it. Have you seen anything, Alex?
No, not really. And on the dark energy front, the most interesting new observation is that the currently measured rate of expansion, the so-called Hubble parameter, is significantly faster at the 5 sigma level than predicted by the cosmic microwave background astronomers. And we're trying to figure out what's going on. We don't think they've done anything wrong or that we've done anything wrong. We think that nature is telling us something interesting. And maybe that interesting thing is that there was an early form of dark energy that gave the universe a boost or something like that. But that's the new thing in cosmology, is this Hubble tension, it's called.
Yeah. I'm not close enough to have an opinion, but I'm just cheering when people work on it.
Right. So here are some more questions for you, John. What are the most challenging measurements planned for the Webb telescope?
Well, I would say the hardest ones we knew about when we started off was to see the most distant galaxies, because it's hard to find them. It's hard to have a good search strategy to know where to look, and also to look for the little planets. Try to get a spectrum of those little planets as they transit in front of their stars. So we know what we built. It's working beautifully. We don't know what nature did exactly. So now what's the best way to try to find something different when you've never seen it before? Lovely strategy question. So that's what our astronomers do every year. We say, please send us proposals just to, for what we're going to do this year. And we got, I think, 1,600 of them this year, which is immense. So that means that's our method to try to find the most interesting things. Let people tell us.
Yep. I'll feel lucky if mine are accepted. Low odds with that many proposals. So here's a question from Paul Lake. Would it be possible to, say, in 10 years or so, refuel and service the JWST? Good
question. Well, everybody wants to know because we serviced the Hubble, and that's why it worked so well for so long. We did Webb without possibility of doing that. It's no longer completely impossible because we are building rockets that could go there and could take astronauts out there if we want to send them. And we did put a pattern on the end of the Webb telescope so a robotic camera could know what to do. So it's not impossible, but we did not make it easy.
Right. That's too bad. But of course, there were cost-saving measures, and the more bells and whistles and possibilities you put on instruments, the more expensive they become, and then maybe they won't be a reality at all, right?
Yeah, well, but from my perspective, it was more about if you're spending your time and your resources on something that you don't need, then you're increasing your risk of failure.
Right. So here's a question. What are the prospects for space-based long baseline interferometric telescopes?
Oh, well, there are two kinds. One would be the millimeter wave telescopes, which we use to observe the black holes, the Event Horizon Telescope. We definitely could extend into space with orbiting millimeter wave dishes to work with the set that we already have on the ground. So that's definitely something people are studying here at NASA and with the Event Horizon Telescope team. So that's that one. The other possibility is potentially looking for the surface features at shorter wavelengths. So have sketches showing what it would take to study the surface of an exoplanet and actually measure the features on the surface of an exoplanet with 2 telescopes or more combining their beams together. So it's hard, but at least we have some sketches.
Right. Yeah. Easier at radio wavelengths than optical or infrared, that's for sure.
Yeah.
What evidence tells us that dark matter is anything other than black holes and cold neutron stars?
Oh, I'm actually not close to that right now. You would be looking for the effects of individual objects. So how do I know it's not a bunch of little individual objects as compared to just smooth that effect of Einstein's constant? I want to see something that suddenly goes in front of my telescope and disturbs thing. So I want to see a little black hole going and bothering something else, so that I know it's. So we have been watching the sky for this purpose for a long time. We have telescopes that look at all the stars in the center of our galaxy and look for when they change because something is going in front of them. And so what we've seen so far is chance coincidences when a star goes in front of another star, and we see that. So far, there's no sign that any of those are little bitty black holes. So that's the test that we have at the moment that I think is interesting.
Yeah, if I could add to that, John, you know, the early universe in the first few minutes produced hydrogen, helium, and their various isotopes. And it turns out that the proportions in which those things were produced are dictated very strongly by the amount of protons and neutrons in what we call baryonic matter. And that predicts a certain amount, which is much, much less than the amount of dark matter we infer from galaxy motions and gravitational lensing and so on. And the other thing is that a detailed study of the microwave background fluctuations that John and George Smoot discovered also gives a constraint on how much of this baryonic dark matter there could be. And again, it's 5% of the cosmic pie, 25% is non-baryonic dark matter, and 70% is dark energy. But that goes along with what John was saying, that we're not seeing gravitational lensing from, you know, cold neutron stars or black holes or anything like that. So those are the different lines of evidence.
Yeah.
I'm
sure you people have been looking.
Yeah.
Because it would.
Definitely. Here's one from Richard Miles.
We would love nothing more than to prove our buddies are wrong.
Absolutely. Here's one from Richard Miles. What political hoops did you have to jump through to get Webb launched?
Oh my goodness. Well, I didn't do the jumping. So, but I'll tell you just briefly that more than once we realized that we didn't have nearly enough budget and time to do what we said we wanted to do. And so what's had to happen was NASA had to get some external reviewers to come say, is this a good project or not? And the upshot was the committees said every time, yes, it's a good project. It's much harder than they thought. And they should have asked for more time and more money. And that's about as good a report as you could possibly get. So that enabled Congress to say, okay, we will not pull the plug. We will continue. And so that was really important. So it was not me jumping through a hoop. It was asking for help from external world. Tell us if we're doing okay or not. And the answer was, yeah, did good work, didn't ask for enough money.
Good one. Well, it's great that you succeeded, John. Here's the question. In that we are presumably not at the center of the universe, are there directions to look that are more distant than looking in other directions? And how does one figure this out?
Oh, good question. As far as I know, we have no sign of that. So how would you know? You would look for the map of the cosmic microwaves and see if there's anything that's not supposed to be there. So far, it looks like it's just sampling a universe which is very uniform. And within the accuracy we can measure, there's no preferred direction, which is the best we can do to answer this question. It's probably good to remember and remind people, though, that we see the piece of the universe that we can see. And so we're kind of imagining what's way, way, way beyond that. And so, you know, it's simple for astronomers to say, assume the universe is infinite and uniform. And then we can calculate everything from that. But the next question, well, what if it's not exactly, is much harder. And what would the evidence be? And so people have been looking, but so far we haven't found much pattern.
Yeah, and the fact that everywhere we look in each direction, it all looks the same, suggests much more probably that, we're not in the center of some sphere, but that we're just in a random place, and the universe keeps going beyond the observable boundary to which we can see. But whether it's infinite or finite, we do not know. And I don't know of any way that we will ever really know. So,
Yeah, that's what I understand too. So
yeah.
Nobody's got a plan to measure beyond infinity.
Exactly, right. I'd like to ask the audience if there are other questions. Go ahead and put them in that one location, or even, put them in the chat box to everyone, and I could see them there. Because right now I don't see another question.
Well, if I had a question, I would ask, well, what do you think the chatbots will be talking about in 100 years?
Right. What will they be talking about?
I don't know.
Yeah. So, John, going back to what you were saying, at the L2 point, the telescope is not perfectly collinear with the sun and Earth, because then Earth would block the sun and you wouldn't get radiation to the solar panels. Moreover, radio radiation from the sun would be so strong that it would swamp the radio signals from Earth that are sending commands to the Webb. So the Webb is actually undergoing a little so-called halo orbit out there. Can you tell us a little bit about that and how you have to nudge it back in every once in a while?
Yeah, and actually we call it a little halo, but it's actually quite large. As seen from here, it's sort of 20 or 30 degrees radius, which is a lot. So we're not really very close to that Lagrange point. We are quite far from it. So from our perspective, it appears to go around the L2 point twice a year. This is just the epicycles that people wrote about 2,000 years ago, as seen in modern terms. So it's just good old Newton's gravity telling us how things orbit the sun.
Yeah, it's quite counterintuitive, though, that there would be this semi-stable halo orbit out there.
Yeah, so we do have to nudge it every few weeks because it is unstable. And of course, we're really poking at it. We're firing our jets for this or that reason. So we don't want to fall off the top of the hill.
Right, that's right. So a few more questions have come in. There has been some conjecture, Richard Miles says, that another dimension might exist. What do you think?
Well, a lot of people tell me that it's true, that especially elementary particles are well described by additional dimensions that are all wrapped up in tiny curls that are so small we would never perceive them, except through measurements and mathematics. So I think they're probably there, but curled up so small you can't see them. That's my guess.
Great. I think that's probably true too. Just a couple more questions, then we'll wrap up. From Peter Stoll, is adaptive optics beneficial to ground-based telescopes? And is it so good that space-based instruments should only be aimed at the wavelengths blocked by the atmosphere?
Good question. Well, answer is no, it's not that good. We have wonderful adaptive optics systems that work, but they don't get us the wide angle field of view that we can get in space. So we can get a number of arc minutes radius field of view of good performance at best from the ground. Depending on how determined we are with all those sodium laser wavelengths that we're talking about, if you want to do a wide field of view and map a whole lot of the sky at once, you can't do it from the ground to that nearly as well. So the Nancy Grace Roman Space Telescope is a small telescope, 2.4 meters across, and it will get much sharper pictures across the whole sky than that LSST, the Rubin telescope that I showed you, which is 8 meters across, but it has to see through air without adaptive optics. So anyway, there's definitely a very long discussion about what should we do in space and what should we do on the ground. At the moment, the short answer is it's expensive to do something in space. So if you can possibly ever do it on the ground, do it that way first.
Right. How much of the sky can be observed at any particular time to avoid sunlight? Daryl Tinker asks.
Okay, we have a range of angles from the sun we're allowed to look at. It ranges from 85 degrees from the sun to 135. So that's about 35% of the sky at once.
Okay, that's good. And then from Gerald Epstein, probably the last question. If some interesting phenomenon or change is discovered by another observatory, how rapidly can the Webb drop what it is doing and go take a look?
Okay. It takes about 2 days for us to go through the process, which is mostly human time. But we also only talk to it twice a day. So we have to receive your request, talk about it, change the plan, load it up into the computers, send it up, and then wait a little while. So we're not set up for instant action.
Yeah. And just very briefly, I think you covered this, but what causes the 6 spikes on the pictures of some objects and why not on all of them?
Okay, actually there are 6 spikes on all of the objects, but we only see them on the bright ones.